All right, this is kind of a status video showing current status for the RS232 based FujiNet. You can see the RS232 based FujiNet right here. RS232 connector coming out the side. I have USB connected for debugging and power, but otherwise, it's just there. It will need its own power as there is no +5 on the RS232 ports for most serial ports. Anyway, with that, you'll see one of the things that you'll see here is that there is a tool that can take and synchronize the time via NTP and set it to MS-DOS. So again, date and time. There we go. Looking good so far. Now, if I go into my workspace, I've got a handful of things which I've been working on here. Most of this is being uploaded to the RS232 directory, FujiNet-RS232, link in the description. But kind of an idea just to show you where things are at this particular point in time. Of course, you saw the pictures for the ISS version here. This uses CGA here to output interactive map with the position of the ISS. And you can see the little blinks happening here. If I move the FujiNet out of the way, you can see the telemetry position. If I take and press the space bar, whatever, it will update it. It will also update every 60 seconds. And escape brings us back out again. So, again, this is all currently using a particular chunk of code called Fujicom and COM, which are built to use the RS232 routines. So the way that this is actually used is right now, this isn't the final form of where this is all going to go. So this is all very much prototype. It's just enough for me to take and be able to write to work out the protocol bugs and to deal with any issues that may arise with that. But basically, it's just cycling through, doing its thing here. If we take and open up Fujicom, you can see we're doing things like referencing serial ports directly, initializing them. This is very prototypical, so baud rate is forced right now, etc. But all the major functions to implement the protocol are actually implemented inside of Fujicom, such as calculating the checksums for each command frame, and building the internal command to take and send each command frame out and to get a response whenever it's needed. Now, since the original SIO protocol used a command pin, I'm repurposing DTR here to actually get to serve that function, so we can separate out the command frames from the payloads that may or may not be sent. Writing command frames, we desert the DTR once we're done, and then we take and get a response. Now, this is then used to implement Fujicom commands, so we can send commands without payloads. We've got Fujicom command read, so we can send commands that expect a payload to come back to the computer. And this basically just calls Fujicom command, and then if it's okay, then it takes and grabs the payload. Otherwise, we bounce out with the error code that was returned. Write goes the other direction. Write goes from the computer to the FujiNet itself. So it's very much mirroring what's happening in the Atari version here, except this is all happening over RS232. And I had to take and add some additional functionality to the COM port routines that I'm actually using here. These are implemented inside of com.c. And they're interrupt driven. They're pulled from a listing that was written by Mark R. Nelson in 1990, and they use the serial port directly. It does not use any of the FIFOs in the 16550 or anything else, but otherwise it basically just implements an interrupt driven serial port handler. There's nothing all that special about it. So we shouldn't really have too many weird little surprises here. Transmission and receives happen from dedicated 256 byte ring buffers in both directions. It's assumed to be 256 bytes to make the math a bit easier to calculate, you know, the usual stuff. IIR receive, and the one thing that we get interrupts for changes in the line status, changes in the modem status, which are signals like the ring indicator, which we use to indicate whether or not there's traffic or not, and so on. The usual suspects here, set the baud rate, all this stuff. Otherwise, just a pretty straightforward little serial port routine right here. Nothing special. I added some additional routines to change the DTR status so we could implement the command frames. Those just implement the appropriate register writes. And getC sync, which basically sits and waits for data to become available at a port before sending back the resulting character. And finally put, so we can take and do things like output the command frames and stuff as one function. Very basic. So of special note is the way DTR is handled. Ring indicator is handled. Ring indicator is actually used to indicate network traffic. And so that's so you can do efficient use of interactive traffic. Sorry, I'm doing this a little bit out of order. So once I knew that ISS was working and it was parsing data correctly, I went and started building other utilities. Things like being able to grab Nget. Now, this is just an example here. Nget uses an n-colon URL. Now, why n-colon? Well, for two reasons. One, to specify that the URL here it's a network endpoint specifically, but also because we have different network device endpoints here. N is a shorthand for N1. There's N1, N2, N3, N4, and I may go all the way up to N8. We basically are just allocating separate subdevices for each one of these so that you can have multiple network connections happening at the same time, multiplexed across the serial port. But let's take and say Nget, for example. We can use Nget to pull anything from an endpoint. And that can be anything from I'm just going to make CLS so we can see. That could be from HTTPS, for example. And we'll just grab this, which will output into this file right here. Oop, or not. Here, let me take and reset. The firmware is still a little buggy, so expect some things to kind of get hiccupy here. We'll wait for the Wi-Fi light to come back on. Okay, great. So we've transferred some bytes here, sure. So there it is, dumped the file. But this can work for pretty much anything. For example, I could take and transfer the nget.c file or input.c. Let's see, let me think here for a moment. Let me pause for just a second. Okay, good. Sorry, improvising here. Just wanted to make sure that I had something over there. So I could, if I have my local TNFS file server here, and I'll go to my machine over here to the right of me, and I will grab my copy of input.c and put it here. It makes the connection, and in a few moments, or not. Seriously. Okay, so Nget is acting kind of funky. All right, moving on. TNFS adapter needs a little bit of work. Apologies for that, guys. Yeah, the firmware is still very much in flux, and this whole thing is to show where we are at this particular point in time. I'll move on to input. So just like you have Nget or input, it's now you got input as well. So workspace NPUT. Man, it's been one of those days. I've just been debugging all day, and there's still so much to do. But we have, just like we have input, Nget, we have input. And input is the exact opposite of Nget. Source file name on the main system and a destination and the destination URL where we want to put this. So for example, if I want to take and put this here, input.c here, and I'll put that on my TNFS server, I can. It does it, makes the connection, and then transfers the file across. Now, the interesting thing of what's happening here is that the protocol that can be used can be pretty much anything. So if I want to take and put this onto an SMB file share, then I can. Or if I want to take and HTTP put this to a web server, I can. You can pretty much, that's kind of the thing about the network device here, the network device stack on the FujiNet. It's extremely abstracted. So you can basically take and move things from one endpoint to another quite easily. Or if I want to just take and output it to a TCP socket, I can. It really doesn't, you know, or if I want to take and output it over UDP, I can, and so on, and so on, and so on. The different adapters for such. So I've got a basic set of tools here that I can take and do file transfers to and from this machine and, like, for example, my development machine. But there are other things as well. So one of the things that we have here is NC. NC is short for Netcat. And Netcat is the world's simplest little terminal. And the only thing you really need to do is pass NC the URL that you want to spit out, and it will open an interactive terminal session to it and output the data back. And if the endpoint supports sending data back, then anything you type on the keyboard will be sent back. So let's say, for example, you know, I'm just going to do this just as a just as an example. We're going to get back a file listing here as an HTML document. No problem, right? Bam. It does the lookup, okay, boom, bam, boom, and there we go. But also, we can, I keep thinking I'm on Linux, so no problem. So let's do this. Let's go and use the TELNET adapter and go into level 29. Yeah, that works too. And this is being output to the console here, and I have ANSI sys loaded, so yeah, ANSI stuff works fine too. So, enter your username, renew. I'm just gonna... And you'll see, one of the things you'll notice here is that it's not polling constantly for data, which you would think you would need to do over a link like this. But thankfully, what's actually happening is the ring indicator pin is being used to indicate whenever network traffic is happening, and that generates an interrupt, which tells Fujicom that there's traffic, so we're not constantly having to hammer the bus. And the speed that you're seeing here on this particular connection is indicative of the throttling that Fostex is doing on his end here so that he can support a wide variety of different endpoints. We'll take and quit, Okay, fine. Say we're done. And we'll log off. And once the connection drops, it will take and drop us back off to the prompt here. So yeah, here we go. But there's more. I've kind of set some environment variables here, which include my SSH username and password. And so if I connect to my Unix box, my Linux box over SSH, well, I can, no problem. It handles all the negotiation and everything for me automatically. And it's to the ANSI implementation here is kind of odd, but you know, it's working nonetheless. Ooh, okay, yikes! Looks like we got console issues, but that's okay. We'll just Control C there. Oh, I can't. I need to make the Control C here. Oops. But yeah, this is literally just SSH happening over the FujiNet onto the target machine here. I'm going to take and Control Delete. And that's kind of where we'll leave it at the moment. Where I'm actually having issues right now has to do with the way I want to implement this particular implementation. Not by talking over Fujicom, but rather doing a BIOS call to an interrupt that we specify. In this case, let's say F5 by default. Doing a service call, setting up the registers, and then doing an int call for each. So, as an example for that, let's compare. Workspace, and let's go to RS232. I have a particular test program right here, which is implemented using Fujicom. And we'll have a look at it. It just shows the current adapter configuration. It sends a special command to device 70, which is the Fuji device. Every Fuji command has a command frame, and that command frame consists of the device you want to talk to, the command you want to send, and two auxiliary parameters that you can take and set, which define additional parameters that you can send for additional functions, whatever. So we'll see right here that we're sending out this command and we're using read to get back whatever it sends back. And in this case, it will take and send back a binary structure that corresponds to all of the networking information that's up here. It does that, and then I take and display the result, right? Pretty straightforward. And then when I'm done, I take and close the COM port, and that's it, right? So if I take and run this, we'll see that this works as expected. I can keep running this over and over and over again, and I can consistently get my networking information just fine. However, let's compare and contrast this to what I call experiment number 1. This is BIOS experiment number 1, and it corresponds with a handful of different pieces here. Fuji BIOS takes and combines Fujicom right here and sets up essentially an interrupt handler for interrupt F5 here, which we see. We get all our registers here, and then based on that, we take and parry them out according to what we want to do here. In this case, adapter E8, just like this, working in exactly the same way. Get adapter config. I get adapter config, ESBX, and then break, right? So since this is for basic prototyping, we're implementing this as a TSR. So we take and open up the COM port. We disable interrupts real quick so that we can set the vector and then re-enable, and then correspondingly, we take and go do a keep here to keep this program in memory with the 1K stack size. one of the things that happens here as part of our interrupt routine is I immediately take and enable interrupts again so that the serial port can work as quickly as humanly possible. And based on this, we take and do, we dispatch according to our needs here. This is just a prototype. We can find better ways of doing this, of course. No big deal. Get adapter config. So the same thing that we did before in Fujicom, we set up a command frame, and then I pass back the reply, which is a complete here in register AX. Command unsigned, but I put the results in the address specified by segment address ES and offset address in BX. Pretty straightforward, right? Well, if we take run Fuji BIOS, for example, now it's in memory. And if I take and look at test3.c, which is an implementation of exactly the same program as you saw before, the difference is that instead of doing Fujicom calls, we are basically just attempting, actually, sorry, not test, let me look right here real quick. Is this the one? Yeah, this is it. Thanks. Something like that. So yeah, we do an int F5, we grab it, and then we see where this actually winds up. And one of the things that happens, our info doesn't wind up where it's supposed to go. God, sorry, I've been making so many changes in rapid succession that I've forgotten where I left off. We can even look at this from a point of view in debug.com. You can see right here, it's just a simple little call where we call EH 0120, call int F5, and then return. Now in this case, when we take and call this here from debug, it's actually going to take and hang because it's waiting for data transmission to complete. We'll do it anyway. Bam, you saw the blink start to happen, but it didn't complete for whatever reason. And if you run test 3, which does the test, it completes the test, but no data shows up in the buffers. This is what I'm currently trying to work through, because if I can get the BIOS implementations to work as expected, then it doesn't matter if you're running the RS232 version of FujiNet or if you're going to be running an ISA-bus version of FujiNet, whatever, it's all going to be using the same calling structure. So I hope this makes sense. So with that, I am, okay, I'm going to call this video here. We're done. And so onward and upward.